देश मेरे तेरी शान पे सदके कोई धन है क्या तेरी धूल से बढ़ के तेरी धूप से रोशन तेरी हवा पे जिंदा तू बाग है मेरा मैं तेरा परिंदा. Hello friends, I hope now your mind is refreshed. So let us start the G.C. Leong Geography book, chapter number 14. The atmosphere. The atmosphere is made up of gases and vapor and receives incoming solar energy from the sun, giving rise to what we call climate. We actually live at the bottom of this indefinite layer of atmosphere where the air is densest. Higher up, the air thins out and it is still a matter of conjecture where the atmosphere ends. One estimate puts this limit at about 600 miles above sea level. The lowest layer in which the weather is confined is known as the troposphere. It extends from the Earth's surface for a height of 6 miles, and within it, temperature normally falls with increasing altitude. The climatic elements such as temperature, precipitation, clouds, pressure, and humidity within the troposphere account for the great variations in local climate and weather that play such a great part in our daily lives. From analysis taken in different parts of the globe, it is found that the lower part of the atmosphere contains a consistent proportion of certain gases. 78% of nitrogen, 21% of oxygen, 0.03% of carbon dioxide, and minor traces of argon, helium, and other rare gases. In addition, it has an unpredictable proportion of water, existing either as a gas like water vapor, a liquid like rain, clouds and sleet, or a solid like snow and hailstones, as well as other solid particles like smoke and dust. It is because of the variable water content of the atmosphere that we have such great constants in weather and climate over different parts of the world. If we were to live in a dry atmosphere absolutely without water, there would be no weather and not even much climate. Above the troposphere lies that stratosphere, or the upper layer of the atmosphere. It extends upwards for another 50 miles or even more. It is not only very cold but cloudless, with extremely thin air and without dust, smoke, or water vapor, but there are marked seasonal temperature changes. Beyond the stratosphere is the ionosphere, which goes several hundred miles up. It has electrically conducting layers which make short wave radio transmission possible over long distances. Modern artificial satellites launched in the upper strata of the atmosphere, as well as balloons, are used to transmit back to Earth valuable information regarding the conditions of the atmosphere. Insolation. The only source of energy for the Earth's atmosphere comes from the Sun, which has a surface temperature of more than 10,800 degrees Fahrenheit. This energy travels through space for a distance of 93 million miles and reaches us as solar energy or radiant energy in the process called insolation. This radiation from the sun is made up of three parts: the visible white light that we see when the sun shines, and the less visible ultraviolet and infrared rays. The visible white light is the most intense and has the greatest influence on our climate. The ultraviolet rays affect our skin and cause sunburn when our bare body is exposed to them for too long a period. The infrared rays can penetrate even dust and fog and are widely used in photography. Only that part of the sun's radiation which reaches the earth is called insolation. What matters most is the effect of the atmosphere upon the incoming solar radiation. It is estimated that of the total radiation coming to us, 35% reaches the atmosphere and is directly reflected back to space by dust, clouds, and air molecules. It plays practically no part in heating the earth and its atmosphere. Another 14% is absorbed by the water vapor, carbon dioxide, and other gases. Its interception by the air causes it to be scattered and diffused so that the visible range of the spectrum between the ultraviolet and infrared give rise to the characteristic blue sky that we see above us. The remaining 51% reaches the earth and warms the surface. In turn, the earth warms the layers of air above it by direct contact or conduction, and through the transmission of heat by upward movement of air currents or convection. This radiation of heat by the earth continues during the night. When insolation from the sun cannot replace it, the earth's surface therefore cools at night. The rate of heating effects between land and water surface Land gets heated up much more quickly than the water. Because water is transparent, heat is absorbed more slowly, and because it is always in motion, its absorbed heat is distributed over a greater depth and area. Thus, any appreciable rise in temperature takes a much longer time. On the other hand, the opaque nature of land allows greater absorption, but all the radiant heat is concentrated at the surface, and temperature rises rapidly. Because of these differences between land and water surfaces, land also cools more quickly than water. Now we are going to read elements of climate and factors affecting them. Of the various climatic elements, temperature, precipitation, pressure, and winds are the most important because of their far-reaching global influences. These elements and their distribution, whether horizontal from equatorial to polar regions or vertical from ground to atmosphere, are in one way or another affected by some or all of the climatic factors. Latitude, altitude, continentality, ocean currents, insolation, prevailing winds, slope and aspect, natural vegetation and soil. The first one is temperature. And in the temperature, we are going to read first one. Temperature influences the actual amount of water vapor present in the air and thus decides the moisture carrying capacity of the air. Second, it decides the rate of evaporation and condensation and therefore governs the degree of stability of the atmosphere. Third, as relative humidity is directly related to the temperature of the air, it affects the nature and types of cloud formation and precipitation. Second, factors influencing temperature. The first one is latitude. As explained in chapter 1, due to the Earth's inclination, the midday sun is almost overhead within the tropics, but the sun's rays reach the Earth at an angle outside the tropics. Temperature thus diminishes from equatorial regions to the poles. This is illustrated in figure 107. It shows two bands of rays coming from the sun to two different latitudes on the Earth's surface. Band Ri falls vertically over the equatorial latitudes on surface E. Band R2 falls obliquely over the temperate latitudes on surface T. R1 travels through a shorter distance and its concentrated solar insolation heats up a smaller surface area. Temperature is thus high. On the other hand, R2 travels through a longer distance and much of its heat is absorbed by clouds, water vapor and dust particles. Its oblique ray has to heat up a large area, temperature is therefore low. The second one is altitude. Since the atmosphere is mainly heated by conduction from the earth, it can be expected that places nearer to the earth's surface are warmer than those higher up. Thus, temperature decreases with increasing height above sea level. This rate of decrease with altitude, lapse rate, is never constant, varying from place to place and from season to season. But for all practical purposes, it may be reckoned that a fall of 1 degree Fahrenheit occurs with an ascent of 300 feet, or 0.6 degrees Celsius per 100 meters. It is usually more in summer than in winter. For example, in temperate latitudes, in summer, an ascent of only 280 feet will cause the temperature to drop by 1 degree Fahrenheit, whereas in winter it requires 400 feet. Similarly, the lapse rate is greater by day than at night, greater on elevated highlands than on level plains. In tropical countries where the sea level temperature is 80 degree Fahrenheit, a town that is located at a height of 4,500 feet will record a mean temperature of 65 degree Fahrenheit. The third one is continentality. Land surfaces are heated more quickly than water surfaces because of the higher specific heat of water. In other words, it requires only one-third as much energy to raise the temperature of a given volume of land by 1 degree Fahrenheit as it does for an equal volume of water. This accounts for the warmer summers, colder winters, and greater range of temperature of continental interiors as compared with maritime districts. The fourth one is ocean currents and winds. Both ocean currents and winds affect temperature by transporting their heat or coldness into adjacent regions. Ocean currents like the Gulf Stream or the North Atlantic Drift warm the coastal districts of Western Europe, keeping their ports ice-free. Ports located in the same latitude but washed by cold currents such as the cold Labrador Current of northeast Canada are frozen for several months. Cold currents also lower the summer temperature, particularly when they are carried landwards by onshore winds. On the other hand, onshore westerlies convey much tropical warm air to temperate coasts, especially in winter. The westerlies that come to Britain and Norway tend to be cool winds in summer and warm winds in winter and are most valuable in moderating the climate. Local winds, example Fohn, Chinook, Sirocco, Mistral, also produce marked changes in temperature. The fifth one is slope, shelter, and aspect. A steep slope experiences a more rapid change in temperature than a gentle one. Mountain ranges that have an east-west alignment like the Alps show a higher temperature on the south-facing sunny slope than the north-facing sheltered slope. The greater insolation of southern slope is better suited for vine cultivation and has a more flourishing vegetative cover. Consequently, there are more settlements and it is better utilized than the shady slope. In hilly areas, a hot day followed by a calm, cloudless night during which the air cools more rapidly over the higher ground may induce cold, heavy air to flow down the slope and accumulate at the valley bottom, pushing the warmer air upwards. The temperature may then be lower in the valley than higher up as the slopes as shown in the figure. A reversal of the lapse rate has taken place, and this is called a temperature inversion. The sixth one is natural vegetation and soil. There is a definite difference in temperature between forested regions and open ground. The thick foliage of the Amazon jungle cuts off much of the incoming insolation, and in many places, sunlight never reaches the ground. It is, in fact, cool in the jungle, and its shade temperature is a few degrees lower than that of open spaces in corresponding latitudes. During the day, trees lose water by evapotranspiration so that the air above is cooled, relative humidity increases, and mist and fog may form. Light soils reflect more heat than darker soils, which are better absorbers. Such soil differences may give rise to slight variations in the temperature of the region. As a whole, dry soils like sands are very sensitive to temperature changes, whereas wet soils like clay retain much moisture and warm up or cool down more slowly. Now we are going to read precipitation. Types of precipitation. If air is sufficiently cooled below dew point, tiny drops of water vapor will condense around dust particles. When they float about as masses of minute water droplets or ice crystals at a considerable height above sea level, they form clouds, cirrus, cumulus, or stratus. When condensation occurs at ground level without necessarily resulting in rain, haze, mist, or fog are formed. In higher latitudes or altitudes, where condensation of water vapor may take place in the atmosphere at temperatures below freezing point, snow falls either as feathery flakes or individual ice crystals. If the moist air ascends rapidly to the cooler layers of the atmosphere, the water droplets freeze into ice pellets and fall to the earth as hail or hailstones. As more and more supercooled water drops accumulate around a hailstone, it increases steadily in size. Some of them weigh as much as 2 pounds. In a severe hailstorm, the hailstones do great damage to crops and buildings. Very often, the ice pellets exist as frozen raindrops, melting and refreezing on their way down. This forms sleet. It is only when the droplets in clouds coalesce into larger drops between 0.2 mm and 6 mm that rain falls. Now we are going to read rainfall. Types of rainfall. There are three major types of rainfall. The first one is convectional rainfall. This type of rainfall is most common in regions that are intensely heated, either during the day, as in the tropics, or in the summer, as in temperate interiors. When the Earth's surface is heated by conduction, moisture-laden vapor rises because the heated air always expands and becomes lighter. Air rises in a convection current after a prolonged period of intense heating. In ascending, its water vapor condenses into cumulonimbus clouds with a great vertical extent. This probably reaches its maximum in the afternoon when the convectional system is well developed. Hot, rising air has great capacity for holding moisture, which is abundant in regions of high relative humidity. As the air rises, it cools, and when saturation point is reached, torrential downpours occur, often accompanied by thunder and lightning. The summer showers in temperate regions are equally heavy with occasional thunderstorms. These downpours may not be entirely useful for agriculture because the rain is so intense that it does not sink into the soil but is drained off almost immediately. The second one is orographic or relief rain. Unlike convectional rain, which is caused by convection currents, orographic rain is formed wherever moist air is forced to ascend a mountain barrier. It is best developed on the windward slopes of mountains where the prevailing moisture-laden winds come from the sea. The air is compelled to rise as shown in figure and is thereby cooled by expansion in the higher altitudes and the subsequent decrease in atmospheric pressure. Further ascent cools the air until the air is completely saturated, relative humidity is 100%, condensation takes place, forming clouds and eventually rain. Since it is caused by the relief of the land, it is also known as relief rain. Much of the precipitation experienced on the windward slopes of the northeast of West Malaysia, western New Zealand, western Scotland, and Wales, and the Assam hills of the Indian subcontinent is relief rain. On descending the leeward slope, a decrease in altitude increases both the pressure and the temperature. The air is compressed and warmed. Consequently, the relative humidity will drop. There is evaporation and little or no precipitation. The area in the lee of the hills is termed the rain shadow area. The effects of rain shadow are felt on the Canterbury Plain of South Island, New Zealand, and the western slopes of the northern and central Andes, and in many other areas. The third one is cyclonic or frontal rain. This type of rainfall is independent of relief or convection. It is purely associated with cyclonic activity, whether in the temperature regions, depressions, or tropical regions, cyclones. Basically, it is due to the convergence, meeting of two different air masses with different temperatures and other physical properties. As cold air is denser, it tends to remain close to the ground. The warm air is lighter and it tends to rise over the cold air as shown in figure. In ascent, pressure decreases. The air expands and cools, condensation takes place, and light showers called cyclonic or frontal rain occur. The heavier and colder air masses eventually pushes up the warmer and lighter air, and the sky is clear again. Now we are going to read pressure and planetary winds. World pressure belts. We studied in chapter 11 the circulation of waters in the oceans and noted that they follow a regular pattern, flowing from the poles equatorwards and from the equator polewards. In the same way, there is also a circulation of the air over the surface of the earth caused by the differences in pressure. Along the equator and within 5 degrees north and south is the equatorial low pressure belt, where there is intense heating with expanding air and ascending convection currents. This equatorial belt is often termed the doldrums because sailors in the olden days often found themselves becalmed here. It is a zone of wind convergence. About 30 degrees north and south occur the subtropical high pressure belts where the air is comparatively dry and the winds are calm and light. It is a region of descending air currents or wind divergence and anticyclones. It is frequently referred to as the horse latitudes. Around the latitudes 60 degrees north and south are two temperate low pressure belts which are also zones of convergence with cyclonic activity. The subpolar low pressure areas are best developed over the oceans where temperature differences between summer and winter are negligible. At the north and south poles 90 degrees north and south where temperatures are permanently low are the polar high pressure belts. Unlike the water masses of the high latitudes in the southern hemisphere, high pressures of the corresponding latitudes in the northern hemisphere are a little complicated by the presence of much land. Some pressure differences between summer and winter can be expected. Now, the planetary winds. Within this pattern of permanent pressure belts on the globe, winds tend to blow from the high pressure belts to the low pressure belts, the planetary winds. Instead of blowing directly from one pressure belt to another, however, the effect of the rotation of the Earth, Coriolis force tends to deflect the direction of the winds. In the northern hemisphere, winds are deflected to the right, and in the southern hemisphere to the left, as shown in the figure. This is known as Ferrell's. You can see here the picture. Ferrell's law of deflection. The Coriolis force is absent along the equator but increases progressively towards the poles. For this reason, winds blowing out from the subtropical high pressure belt in the northern hemisphere towards the equatorial low become northeast trade winds, and those in the southern hemisphere become the southeast trade winds. These trade winds are the most regular of all the planetary winds. They blow with great force and in a constant direction. They were thus helpful to early traders who depended on the wind when sailing the high seas, hence the name trade winds. Since they blow from the cooler subtropical latitudes to the warmer tropics, they have great capacity for holding moisture. In their passage across the open oceans, they gather more moisture and bring heavy rainfall to the east coast of the continents within the tropics. As they are offshore on the west coast, these regions suffer from great aridity and from the trade wind, hot deserts of the world, example the Sahara, Kalahari, Atacama, and the Great Australian Deserts. From the subtropical high pressure belts, winds blow towards the temperate low pressure belts as the variable westerlies. Under the effect of the Coriolis force, they become the southwesterlies in the northern hemisphere and the northwesterlies in the southern hemisphere. They are more variable in the northern hemisphere, but they play a valuable role in carrying warm equatorial waters and winds to western coasts of temperate lands. This warming effect and other local pressure differences have resulted in a very variable climate in the temperate zones, dominated by the movements of cyclones and anticyclones. In the southern hemisphere, where there is a large expanse of ocean from 40 degrees south to 60 degrees south, westerlies blow with much greater force and regularity throughout the year. They bring much precipitation to the western coast of continents. The weather is damp and cloudy and the seas are violent and stormy. It is thus usual for seafarers to refer to the westerlies as the roaring 40s, furious 50s, and shrieking or stormy 60s, according to the varying degree of storminess in the latitudes in which they blow. It must be pointed out that not all the western coasts of the temperate zone receive westerlies throughout the year. Some of them, like California, Liberia, Central Chile, Southern Africa, and the southwestern Australia receive westerlies only in winter. This is caused by the shifting of the wind belts of such regions, which lie approximately between the latitudes 30° and 40° north and south. Due to the Earth's inclination, as explained in Chapter 1, the Sun is overhead at midday in different parts of the Earth at different seasons. The entire system of pressure at wind belts follows the movement of the midday sun. In June, when the overhead sun is over the Tropic of Cancer, all the belts move about 5 to 10 degrees north of their average position. The Mediterranean parts of the southern continents then come under the influence of the westerlies and receive rain in June, winter in the southern hemisphere. In the same manner, when the sun is overhead at the Tropic of Capricorn in December, all the belts swing 5 to 10 degrees south of their average position. The Mediterranean parts of Europe and California then come under the influence of the westerlies and receive rain in December, winter in the northern hemisphere. This is illustrated in the figure. Lastly, mention must be made of the polar easterlies, which blow out from the polar high pressure belts towards the temperate low pressure belts. These are extremely cold winds as they come from the tundra and ice cap regions. They are more regular in the south than in the north. Now we are going to read land and sea breezes and monsoons. Land and sea breezes are in fact monsoons on a smaller scale. Both are basically caused by differential heating of land and sea, the former in a diurnal rhythm and the latter in a seasonal rhythm. During the day, the land gets heated up much faster than the sea. Warm air rises, forming a region of local low pressure. The sea remains comparatively cool with a high pressure, so a sea breeze blows in from sea to land. Its speed or strength is between 5 to 20 meter per hour, and it is generally stronger in tropical than in temperate regions. Its influence does not normally exceed 15 miles from the coast. It is most deeply felt when one stands facing the sea in a coastal resort. At night, the reverse takes place. As the land cools down much faster than the sea, the cold and heavy air produces a region of local high pressure. The sea conserves its heat and remains quite warm. Its pressure is comparatively low. A land breeze thus blows out from land to sea. Fishermen in the tropics often take advantage of the outgoing land breeze and sail out with it. They return the next morning with the incoming sea breeze, complete with their catch. Land and sea breezes are illustrated in the figure. In the same way, monsoons are caused. Rapid heating in the hot summer over most parts of India, for example, induces heated air to rise. The southwest monsoon from the surrounding ocean is attracted by the low pressure over the land and blows in, bringing torrential rain to the subcontinent. Similarly, in winter, when the land is cold, the surrounding seas remain comparatively warm. High pressure is created over Indo-Pakistan and the northeast monsoon blows out from the continent into the Indian Ocean and the Bay of Bengal. Now we are going to read the Fawn wind or Chinook wind. Both the Fawn and Chinook winds are dry winds, experienced on the leeward side of mountains when descending air becomes compressed with increased pressure. The Fawn wind is experienced in the valleys of the northern Alps, particularly in Switzerland in spring. Chinook winds are experienced on the eastern slopes of the Rockies in USA and Canada in winter. As illustrated in the figure, air ascending the southern slopes of the Alps expands and cools. Condensation takes place when the air is saturated. Rain and even snowfall on the higher slopes. In descending the northern slope, the wind experiences an increase in pressure and temperature. The air is compressed and warmed. Most of its moisture is lost and the wind reaches the valley bottom as a dry, hot wind, the Fawn. It may raise the temperature by 15 to 30 degrees Fahrenheit within an hour. It melts snow and causes avalanches. In North America, it is called Chinook, meaning the snow eater. But it has its blessings too. It hastens the growth of crops and fruits and thaws the snow-covered pastures. In the Rockies, the Chinook has been known to raise temperature by 35 degrees Fahrenheit within 15 minutes. The occurrence of frequent Chinooks means winter is mild. Now we are going to read cyclonic activity. Tropical cyclones, typhoons, hurricanes, and tornadoes. All these are different kinds of tropical cyclones. They are well developed low pressure systems into which violent winds blow. Typhoons occur in the China Sea, tropical cyclones in the Indian Ocean, hurricanes in the West Indian Islands in the Caribbean, tornadoes in the Guiana lands of West Africa and the southern USA, in which the local name of whirlwind is often applied, and willies occur in northwestern Australia. Typhoons occur mainly in regions between 6 and 20 north and south of the equator and are most frequent from July to October. In extent, they are smaller than temperate cyclones and have a diameter of only 50 to 200 miles, but they have a much steeper pressure gradient. Violent winds with a velocity of over 100 meter per hour are common. The sky is overcast and the torrential downpour is accompanied by thunder and lightning. In the wake of the typhoon, damage is widespread. Example, in 1922, a typhoon that hurled huge waves onto the Swato coast drowned 50,000 people. The other tropical cyclones have similar characteristics and differ perhaps only in intensity, duration, and locality. Hurricanes have calm, rainless centers where the pressure is lowest, about 965 MB. But around this eye, the wind strength exceeds force 12 of the Beaufort scale, 75 meter per hour. Dense dark clouds gather and violent stormy weather lasts for several hours. A terrible hurricane struck Barbados in the West Indies in 1780, which nearly destroyed the whole island, tearing down buildings and uprooting trees. About 6,000 inhabitants were reported dead. Tornadoes are small but very violent tropical and subtropical cyclones in which the air is spiraling at a tremendous speed of as much as 500 meters per hour. A tornado appears as a dark funnel cloud 250 to 1400 feet in diameter. As a tornado passes through a region, it writhes and twists, causing a complete devastation within the limits of its passes. There is such a great difference in pressure that houses virtually explode. Tornadoes are most frequent in the spring but can occur at almost any time. Fortunately, they are not common in many countries and their destructive effects are confined to a small area. Tornadoes are most typical of the USA and occur mainly in the Mississippi Basin. Now we are going to read cyclones. These are better known as depressions and are confined to temperate latitudes. The lowest pressure is in the center and the isobars as shown in the climatic charts are close together. Depressions vary from 150 to 2000 miles in extent. They remain quite stationary or move several hundred miles in a day. The approach of a cyclone is characterized by a fall in barometric reading, dull sky, oppressive air, and strong winds. Rain or snow falls, and the weather is generally bad. Wind blows inwards into the regions of low pressure in the center, circulating in anti-clockwise direction in the northern hemisphere and clockwise in the southern hemisphere. Precipitation resulting from cyclonic activities is due to the convergence of warm tropical air and cold polar air. Fronts are developed and condensation takes place, forming either rain, snow, or sleet. Now we are going to read anticyclones. These are the opposite of cyclones, with high pressure in the center and the isobars far apart. The pressure gradient is gentle and winds are light. Anticyclones normally herald fine weather, skies are clear, the air is calm, and temperatures are high in summer but cold in winter. In winter, intense cooling of the lower atmosphere may result in thick fogs. Anticyclonic conditions may last for days or weeks and then fade out quietly. Winds in anticyclones blow outwards and are also subject to deflection, but they blow clockwise in the northern hemisphere and anti-clockwise in the southern hemisphere. Now we are going to read climatic types and natural vegetation. It is necessary to divide the world into several climatic zones, each with its own climatic characteristics, natural vegetation, forests, grasslands or deserts, crops, animals and human activities. Though the geographical characteristics may not be absolutely uniform in each climatic type, they have many things in common. Figure gives the scheme of the world's climatic types with their seasonal rainfall and natural vegetation. You can see here the world climatic types chart. So with this our chapter ends, and in the next video we will read the next chapter. So till then, study well, listen to the audiobooks. Thank you.